Hello everyone, welcome to the channel Unknown Physics. Today we'll be going to do a new paper, Thermodynamics, and I'm going to deal with these topics today. So, what is thermodynamics? A branch of physics which deals with the dynamics of a thermodynamic system associated with a thermal energy. It can be any type of energy. So, here it is thermal energy. So, we need to know what is a thermodynamic system. Thermodynamic system is of three types. The first is isolated, then the closed system and the open system. Isolated system. There is no exchange of energy and matter. In a closed system, there is only exchange of energy. In an open system, there is exchange of both energy and matter. So, we need to represent a thermodynamic system. So, we need a variable to represent the thermodynamic system. For example, take a room. The room may contain n number of particles, the volume occupied by each particle and energy of the particle. So, these are for the whole system. These variables describe the state of the system. So, the variable required to describe the state of the system in this case is macroscopic variable. So, this is for the whole system. Next one is the microscopic variable. These variables describe the one particular state of the system. For example, it describes the position and momentum. So, in a classroom, there are students sitting in each row. So, in the second row, the third student. So, it describes the position and the momentum of the student. And the next here is we are going to deal with macroscopic variables. It has two types, extensive variable and intensive variable. Extensive variable depends on mass. Intensive depends independence of mass. Here the examples are energy, number, volume and entropy. In intensive variable, pressure, temperature, density, refractive index. You may think how density is an intensive variable since it has mass in its formula. Density is equal to mass by volume. So, extensive by extensive will give you an intensive variable. And extensive variable is the total of the system. So, E will be equal to E1 plus E2 plus E3. Similarly, entropy. So, all extensive variables are additive in nature. Here, take P naught as the pressure at sea level. And there is a depth or a height as represented as H. So, the pressure is P. So, pressure P will be equal to P naught plus rho GH. So, when you move towards downward, the pressure increases. And when you move upwards, the pressure decreases. So, here the pressure varies with respect to space. So, intensive variables vary spatially. And this has no additive property. Next is the calorimetry. So, the basic definition here is heat capacity. For example, I have a system and I want to increase the temperature of the system by 1 degree Celsius. So, I have to apply some energy to the system, which is the heat energy over here. So, heat capacity is defined as the amount of heat energy required to raise the temperature of the body by 1 degree Celsius, which is Q by delta T. Next is the specific heat. Heat capacity per unit mass. So, S is equal to heat capacity Q by delta T into 1 by M. So, Q is equal to M into S into delta T. And here for example, specific heat of water is 1 calorie per gram centigrade. And for ice, specific heat is 0.5 calorie per gram centigrade. So, molar specific heat. Heat capacity per unit mole. So, C is equal to Q by delta T into 1 by N. So, Q is equal to N C delta T. So, at constant volume, Q is equal to N CV into delta T, and at constant pressure, Q is equal to N Cp into delta T, where Cv is the specific heat at constant volume and Cp is the specific heat at constant pressure. So, the next topic is principle of calorimetry. This is very important. Here I am going to talk about the equilibrium state. Let me take two thermodynamic systems and I am going to join these two thermodynamic systems together. The heat energy is exchanged between these two systems. So, one system may lose the energy and one system may gain the energy. So, when two bodies of different mass and volume join together, there is either heat energy lost or gained. So finally the amount of energy gained or lost must be equal to 0. So the total amount of heat energy delta Q is equal to 0. Heat loss is always negative and heat gained is always positive. So since there are two systems, delta Q1 plus delta Q2 is equal to 0. I can write this as integral dq1 plus integral dq2 is equal to 0. We know Q is equal to ms into delta T. So ms into dt and m2s2 into dt. So this 1 represents for the first system and this 2 represents for the second system. So integrating dt we get t. So m1s1t and m2s2t. So by applying the limits I get m1s1 t minus t1 plus m2s2 t minus t2. Now I am splitting the terms. So m1s1t and so on we get it. So I am writing t terms on one side and t1 t2 terms on the other side. So 2 into t into m1 plus m1 s1 plus m2 s2 will be equal to m1 s1 t1 plus m2 s2 t2. So the equilibrium temperature at last we get T is equal to m1 s1 t1 plus m2 s2 t2 divided by m1 s1 plus m2 s2. So whenever two bodies of different mass, different specific heat combine at temperature T1 and T2, we get the equilibrium temperature. T is equal to m1 s1 T plus m2 s2 T2 by m1 s1 plus m2 s2. So the conclusion here I am going to give is, when two thermodynamics body of different mass, different specific heat and different temperature, then their equilibrium temperature will be T is equal to m1 s1 t1 plus m2 s2 t2 by m1 s1 plus m2 s2. In terms of molar specific heat, T will be equal to n1 c1 t1 plus n2 c2 t2 by n1 c1 plus n2 c2. So here when mass m1 m2 are equal and s1 s2 are equal, there is a similar body problem. For example, we can take one water and water combined together, then T will be equal to T1 plus T2 by 2. Now let's see a problem. A vessel has two compartments of volume V1 V2 containing an ideal gas at pressure P1 and P2, temperature T1 and T2. If the walls separate, the compartment is removed, resulting equilibrium temperature. So this is the system, and there, since it is same gas, for same gas always C1 is equal to C2 and S1 is equal to S2. They have given all these data in the question. So now the equilibrium temperature will be equal to, T will be equal to N1 C1 T1 plus N2 C2 T2 by N1 C1 plus N2 C2. So since C1 and C2 are equal, T will be equal to N1 T1 plus N2 T2 by N1 N2. But this is not the answer what we are expecting, because your question is not in terms of N1 and T1. So we know for an ideal gas PV is equal to nRT. So P1 V1 is equal to N1 RT1, P2 V2 is equal to N2 RT2. So T will be equal to P1 V1 plus P2 V2 by P1 V1 by T1 plus P2 V2 by T2. By rearranging and substituting we will get this. Always express the answer in terms of given variables in the question. Next question. Two thermally isolated systems have heat capacities where C is equal to beta T cube, beta is greater than 0. Initially the two systems are at temperature T1 and T2 respectively, and N1 and N2 will be equal to 1. The system brought in thermal contact and allowed to reach thermal equilibrium. Find the equilibrium temperature. We know specific heat Q is equal to Nc delta T. So dQ will be equal to Nc dt. So by the principle of calorimetry, integral Nc dt, that is from T1 to T, and integral T2 to T Nc dt. T1 is the initial temperature of first system and T2 is this for second system. They are given C is equal to beta T cube. So substituting that, and also they are given N1 N2 is equal to 1. And integrating we will get T cube as T power 4 by 4. So by rearranging all this and substituting the limits, at last we will get this equation. So the equilibrium temperature is T power 4 is equal to T1 power 4 plus T2 power 4 by 2. So this is the answer. And there is a very small concept left and few problems which I will continue in my next video. Thank you so much for watching. Have a nice day.